Hello everyone, welcome to lecture 15 on Mechanics and Materials 1. In this lecture we talk about torsion. This is our last lecture on the topic torsion. We cover sections 5.8 and 5.9 of the Hibbeler book. In particular, we deal with stress concentration and inelastic torsion in sections 5.8 and 5.9 respectively. So stress concentration. If you remember from axial loading, stress concentration occurs due to geometrical imperfections such as changes in cross-sectional area. And for a torsion problem, we also have exactly the same scenario. And for that matter, basically, you can define a torsional stress concentration factor K, which would be basically the ratio of the stress concentrated or the maximum stress due to stress concentration divided by maximum stress if you did not have a stress concentration. The good news is that similar to axial loading, the stress concentration factor also in a torque related problem or in torsion, it depends on geometry. And basically what that means is that for different geometries or dimensions, you can calculate the stress concentration factor. The graph here shows you the stress concentration factor, for instance, for a shaft. So the shaft has two different cross sections that are distinguished by small letter d and capital letter D. Capital D is the larger diameter, small d is the diameter of the smaller part of the shaft, and R is the fillet radius between basically the two. On the horizontal direction, you have the ratio R over D, and on the vertical direction, you have the stress concentration factor. Again, pay attention that stress concentration factor in this context is also shown by the letter K, like we did for axial loading, but this is not the same table. This is not the same graph. So for torsional problem, we have a different graph, and you should come to this and you should read the stress concentration factor from this. But similar to before, you can see that if we have a very small notch radius or fillet radius, you get a very large stress concentration factor. So in the limit, if you have a very, very sharp corner, your stress concentration factor tends to infinity. So this is something that we also learned, for instance, in axial loading, and it makes sense. And basically the message for you is that do not forget to have a proper fillet radius. Another thing is that if the ratio between capital D and small d is increasing, you would also observe an increase in the stress concentration factor. And that also makes sense because in the limit, you can imagine if D over D is 1, you would have no stress concentration factor because this would be a uniform shaft. Okay, so now that we have this graph, we want to know how to design a shaft using this. Recall the formula for maximum shear stress if we did not have a stress concentration factor. So if this is for a uniform shaft, if you want, there is no stress concentration yet. And this is what we have done before. And if you remember, based on the formula that we have here, so maximum shear stress would be torque times maximum radius C divided by J, and J is the polar moment of inertia. If you look at this, then you get the toe max at the outer radius, which is R max, or otherwise denoted as C. So that's your toe max. Now, the stress distribution itself, it follows this formula, or maybe you just remember it as tau equals R divided by C tau max. So you can see that you would have a linear distribution of stress. Now, this is valid for a uniform shaft without any change of area. This is what we have done before, but for a shaft that we had just seen in the previous picture, so if it has, let's say, two different cross-sectional areas, so something like this. So if you think of a shaft which looks like that, now here you would have a stress concentration. And if you draw the stress distribution on that inner shaft, on the thinner part of the shaft, this is what you would see. This is the shear stress distribution. So the blue one here, it shows just a regular case. So the blue one here is exactly what we had here. And just for the purpose of comparing them, I draw them on top of one another. So here you can see that if you have a stress concentration, your tau max is larger than what you would have had before for maximum shear stress. And the ratio between the two, so again, this is the maximum shear stress that you would have had for a uniform shaft. The ratio between the two is the stress concentration factor. Or otherwise, if you want to calculate the maximum shear stress, if you have a stress concentration factor, you just multiply stress concentration factor times Tc over J. And obviously, you can imagine that in this case, when you get a tau max, you also lose the linear distribution of the stress. So you wouldn't get something like this, obviously, because you can imagine the torque that you are applying in both cases, they are equal. And if you remember, you could calculate torque by integrating the relation like this over the cross-sectional area. So you can imagine if for the same torque, when the maximum torque is more than what you had before, then somewhere inside you should get less stress than before. So you get basically something like this. So this is now your actual shear stress distribution caused by a stress concentration, which you should compare it with a uniform distribution if you did not have a stress concentration. Okay, so that's it. And what we want to do next is to better understand it by an exercise together. Exercise 1 in this lecture is similar to problem 513 on page 240 of the book. The shaft shown in the figure is supported by bearings at A and B. So you have two bearings at A and B, and then there is a shaft between the two. Determine the maximum shear stress in the shaft. The fillet radius at the junction of each shaft is 6 millimeter. So here and on the back, basically, you know that the fillet radius is 6 millimeter, and you are asked to calculate the maximum shear stress in the shaft. So we know that we are going to need the stress concentration factor, and if you remember, to calculate the stress concentration factor or to read it from the graph, we needed two ratios. We needed the ratio of the two diameters, capital D divided by small d. In this case, this would be your capital D, this is your small d. So we would need that ratio, which is basically 40 divided by 20, or 40 and 20 are radius, so you can multiply them by 2, but then the ratio is still the same. So capital D divided by small d is 2. That's the ratio of the diameters. And then you also need the ratio of the fillet radius divided by the diameter of the smaller part, or thinner part of the shaft, and that was 6 millimeter divided by 2 times 20, which is, again, 20 is the radius, so 2 times 20 is 40 is the diameter, and R over D would be 0.15. So with these two, you can use the graph that we had previously. You can basically draw the vertical line here at R over D 0.15, and then you draw a horizontal line from the point that it intersects the line with d over d divided by 2. So you come back to the vertical axis and you read the stress concentration factor, that is in this case 1.3. So all you have to do is now to use the formula that we introduced earlier. Tau max is K, the stress concentration factor that we know now, times torque, that is 30 Newton meter, times C, that is the maximum radius at the thinner part, 0.02, divided by J. And then again, J is also corresponding to the thinner part of the shaft. So basically, you want to calculate the maximum stress for the thinner part and then multiply that by stress concentration factor. If you do that, you get 3.10 megapascal. You can imagine that for any shaft design like this, if you wanted to calculate the same thing for the thicker part, you would get a smaller number, because you know J is proportional to C to the power of 4. So basically, increasing the diameter or increasing radius, it gives you a smaller number. So we always calculate it for the thinner part and then multiply that by stress concentration factor to get the maximum shear stress. Now, if you want to also draw the shear stress distribution, you can see that the shear stress distribution predicted by torsion formula. So if we did not have a stress concentration factor, here you get your common linear distribution, which would look like this. But then again, because now we have a maximum shear stress, the actual shear stress distribution would look like this. The next topic that we would like to talk about is inelastic torsion. So inelastic torsion is relevant for ductile shafts or ductile materials in general. And you remember, if you have a ductile material as opposed to a brittle material, if you have a ductile material, you should also carry out a plastic analysis. Okay, so the material behavior is no longer our simple linear elastic behavior. We also have the so-called elastoplastic behavior. And if you remember, we said we always talk about perfect plasticity in the sense that if the material reaches the yield limit, it would just have a constant stress. Now, the elastoplastic behavior for perfect plasticity, in terms of normal stress-strain relationship, it's shown here. So you would have sigma epsilon graph, but you can also draw the same thing for shear stress and strain. In which case, again, for the linear case, you would have shear stress is equal shear modulus times shear strain. And then if you reach the yield limit, it would just remain flat and it would not increase anymore. Another thing that we need to recall is that shear strains develop linearly. So we remember this from what we had done before in the previous lectures. So from the geometrical description of the problem, basically, we learned that shear strain distribution in the shaft is always linear. And it follows the relation gamma equals R divided by C gamma max. And then again, C is R max. So previously, we always said tau equals G multiplied by gamma. And we concluded that tau is linear because gamma was linear. But you can imagine that this behavior and this conclusion is only valid if we are in the linear part of the graph. So if we reach the yield limit, that is no longer a valid conclusion, and we want to talk about that. So basically, we begin with the picture we have, or what remains as before. This is the shear strain distribution. Shear strain distribution does not change whether it's elastic or inelastic torsion. But then again, as we spoke before, if it is elastic, tau equals G gamma. And since gamma is linear, tau will be linear too. And basically for shear stress distribution, you would have the relation tau equals G R divided by C gamma max. This would be your elastic distribution of shear stress. Now, if we increase the stress further, we also reach the yield limit. And when you reach the yield limit, it means that some parts of the material would yield and some parts would still behave linearly. Because the distribution is linear, for instance, you can imagine if at the end you reach plasticity, still inside the stresses are smaller, so they may remain elastic. So if it is inelastic torsion, you would get this sort of combined behavior that you would have a region that reaches plasticity, and for that region you reach the maximum stress tau y, but then inside the stress strain relationship still follows the linear relation that we have tau equals G gamma, as long as that number G gamma is smaller than yield stress tau y. So we want to analyze this problem now. So if I put everything together here again, this is shear strain distribution. This is elastoplastic material behavior. Now, if it was an elastic deformation, stress distribution is simple. It's just tau equals G gamma. But if you reach plasticity, then you can always talk about a region that is still elastic. So we call that elastic core, because until then, stresses are still smaller than yield stress. So here, stresses are smaller and it's still elastic. And then you have this plastic ring around the elastic core. So now for this sort of scenario, or with the information that we can see here, we want to compute torque, and we want to know what happens to the torque. So we begin by our common formula that we had for the torque previously. So torque is the integral of distance times force, dF. And dF is shear stress times dA. dA itself is 2 pi r dr. So if you write the previous relation in terms of r. Now, instead of integrating over a, you would say integrate from 0 to c, and then c is the external radius or maximum radius. So basically, we come up with this relation. T equals 2 pi tau r squared dr from 0 to c. Now, this relation is generic in the sense that we did not use any information from these two figures. So we did not assume anything about the nature of the shear stress yet. So this formula itself is generic. What we want to do now is to use this formula and then compare these two cases. So we begin with the elastic one. So assuming that we have an elastic deformation, we start with our generic formula that we just had, but now we know because it's elastic, you can write shear stress equals G gamma, and then you can write gamma equals R over C gamma max. This is our general relation, so this is always valid and you are allowed to do that. And also you remember gamma max is phi divided by L times C. And phi was the angle of twist, L was the length of the shaft. So if you insert those relations, instead of tau here you have G gamma. Instead of gamma here you have R over C gamma max. And then instead of gamma max, you have phi over, well, basically instead of gamma max divided by C, you have phi over L, which again, we had it here. So if you do that, now you end up with this relation, taking out the constants. And if you pay attention to it, what remains in the integral, and maybe multiplied by 2 pi, it's exactly our definition of the polar moment of inertia. If you want to see it better, maybe you want to write dA again as before as 2 pi r dr, so that you can see that this thing is indeed just r squared dA. So it's the integral of r squared dA. So this is exactly the polar moment of inertia, and basically this brings us to our relation that we had before, T equals G phi J divided by L, or otherwise maybe you just remember it as phi equals TL over GJ. So this is not a big surprise. We just calculated the torque for the elastic case, and we ended up exactly with what we had before, because in the previous lecture we assumed that the shaft remains elastic. So we just recovered what we had before. Now the question is, if you increase the torque, how long does it remain elastic? So what we want to calculate is to find out the maximum elastic torque. Again, we begin with the generic formula that we had before, but now you know that because it is elastic, the stress distribution is linear. But also because you want the maximum elastic torque, you know that tau max should be just the same as yield stress. Okay, so it's just the moment that you reach the yield stress. So basically it means that you can start with this relation, but now for stress distribution, you can just use the relation R divided by C tau Y instead of tau max. And if you do that, you get the maximum elastic torque. And this is exactly what we do. And if you insert that and if you calculate the integral, you end up with this relation for maximum elastic torque. So it's pi over 2 tau y c to the power of 3. Now this relation is important because it tells you that this is the maximum torque you can apply and still the shaft will behave elastically. Or otherwise, it means if you unload the shaft with this much torque, you are always in the elastic regime, and if you go up like this, you come back to the same point. Okay, now that we have the maximum elastic torque, we want to also calculate the elastic plastic torque. So what happens to the torque if we have a scenario like this? So if we have a shaft that is partially plastic and partially elastic. Again, we begin with the generic formula. If you remember, as I mentioned before, this formula is valid regardless of the nature of the stress distribution. But now we define this quantity Ry as the radius of the elastic core. Okay, so basically this is a radius and it's smaller than the elastic. It's smaller than the maximum radius. It's the radius of the elastic core. And you can imagine that if Ry is 0, that means there is no elastic core. So it's all plastic. And if Ry is C, it's all elastic. Okay. So these two limits hold, but then usually we are just assuming that Ry is somewhere between 0 and C, and we want to know what happens then, so that you have an elastic core for the shaft. So if you do that, now the stress distribution within the core, within the elastic core and outside the elastic core is different. So outside the elastic core, or in the plastic ring, you just have a constant stress that is tau y. So instead of integrating from 0 to C, we split the integral from 0 to Ry, which is the elastic part, plus Ry to C, which is the plastic part. That's what we want to do. Now, in the plastic part, tau is constant. It's just tau y. So this is exactly this formula that we had up there, but we replace the shear stress with yield shear stress, tau y. Within the elastic core, however, the stress is linear. So tau would be R divided by Ry times tau y. And then again, you can see if this R, if the radius is exactly Ry, you reach tau y, which is this one. So it's just the moment that it starts being plastic. And then for any other radius, you get the distribution here in the triangle. Okay, so basically that's what we do. We start with the generic formula. We split it into two parts, elastic part and plastic part, or elastic core and plastic ring. So basically this part would correspond to the inner part. This part corresponds to the outer part. And if you integrate that, you end up with this relationship. So T elastoplastic torque for elastoplastic deformation is pi over 6 times tau y, yield stress, times 4 times C cube minus Ry cube. Okay, so this is our elastoplastic torque. Now, remember what we did. We assumed that we apply a torque that is smaller than elastic torque. So we started with a torque which was smaller than elastic torque. And elastic torque was the maximum torque that it was still elastic. Then we increased it to a point that is partially elastic and partially plastic. So the question is now, what happens if we increase the torque? So we want to know what is the maximum torque you can get. And you can imagine if the maximum torque you can get is where everything is plastic. So now we want to calculate the maximum torque or maximum plastic torque. Again, we just call it maximum plastic torque, but this is also our maximum torque. So beyond that, we cannot exceed. Again, we start from the generic formula here. Torque is 2 pi integral from 0 to c tau r squared dr. But now, because you know it's fully plastic, you are talking about a case that there is no elastic core. So basically everything is just tau y. So if you replace the shear stress by the yield stress, you calculate TPL or TP. That's the maximum torque or maximum plastic torque, and that's 2 pi over 3 tau y c cubed. In summary, this was our generic formula for torque, or for the relationship between torque and shear stress. If it is elastic, the maximum elastic torque you can apply is pi over 2 tau y c to the power 3. Elastoplastic torque would be pi over 6 tau y 4c to the power 3 minus ry to the power 3, and tau plastic is 2 pi over 3 tau y c to the power 3. Now we just want to test this and see if this relation can recover the other extremes, the two extremes. So in one extreme, if it is fully elastic, so if you think about this figure, for a fully elastic deformation, it means that your Ry, so the radius of the elastic core, is just the same as C. So if the radius of the elastic core is equal C, and we use this relation, we calculate TEP equals pi over 2 tau y c cubed, which is exactly as T elastic. So that makes sense. On the other hand, just the moment that elastic core vanishes, that would be where we get the maximum torque, and that would correspond to Ry equals 0. So that would be our fully plastic limit. And then again, if you just insert Ry 0 here, this will disappear. So you get 4 divided by 6, which is the same as 2 divided by 3. So you get 2 pi divided by 3 tau y c cubed, and that's exactly the same as TPL. So basically this is how it is. This relation, so elastoplastic torque, it recovers everything that is between the elastic torque and maximum torque, which is the plastic torque. Okay, so this is limited by them, and then you can imagine that in the two limits, in the fully elastic limit, we talk about this one, and then in the fully plastic limit, we talk about this one. So in summary, we can calculate torque also if we have inelastic loading, and we can calculate stress distribution also if we have inelastic loading. So previously, if it was elastic, we had done that. It was a linear distribution, and that's what we did in the previous lecture. But also if it is inelastic, we can still use our knowledge and calculate the torque. The only difference is that in this case, we have a more complex relation, whereas if you remember from the previous lecture, we had something like TR over J. This was only for fully elastic, okay? So for fully elastic, the relation between stress distribution and torque is much easier than the inelastic one, but also for the inelastic case, it is not impossible to find the relation, as we had just seen. So what we want to do next is to look into an exercise together to better understand this. Exercise 2 and the last exercise of this lecture is similar to problem 514 on page 246 of the book. The shaft with the given dimensions in the figure is assumed to have the tau gamma diagram as shown. So the stress-strain distribution for shear stress, shear strain is given in the figure. As you can see, the yield stress, the yield shear stress tau y is 20 megapascal, and that occurs at gamma equals 0.286 times 10 to the minus 3 radian. Determine maximum elastic torque, T elastic. So in part A, we want to calculate T elastic. Maximum plastic torque, T plastic. That's what we do in part B. In part C, we are asked to calculate the minimum shear strain, minimum gamma, at the outer wall to develop a fully plastic torque. So how much rotation or how much shear strain we need at the outer wall to develop a fully plastic torque. The dimensions of the shaft are given here. So 30 and 50 millimeters are the inner and outer radius respectively. So the first thing we want to do in part A is to calculate the elastic torque, T elastic. And for that, we have two ways of calculating that. So the first way is what we had done in the previous lectures. So recall the relation tau equals TR over J. Now in this case, if we want to calculate the maximum elastic torque, that means the T in the relation would be the elastic torque, T elastic. R would be C, that's R max. And if we have R max, then we are talking about the tau max. And now because it is the maximum elastic torque, tau max must be the same as the yield stress tau y. So that's all you have to do. If you insert these numbers, you can calculate T elastic. So from this relation, basically, you can see that T elastic is J times tau max, which is in this case tau y, divided by C. C is the maximum radius, the outer radius in this case, that's 50 millimeter. So it's 0.05. Tau y is 20 megapascal, and J is pi over 2, 50 millimeters squared minus 30 millimeters squared. If you calculate all of that, then the elastic torque would be 3.42 kilonewton meter. So this is what we could have done also in the previous lectures, but alternatively, we learned that we can use this formula. So our generic formula for torque is T equals 2 pi integral from Ci over Co, or integral over the cross section, tau r squared dr. And now because it is an elastic deformation, we know that tau distribution is R over C times tau max. And in this case, again, C is the outer radius. So you can think of the linear distribution like this. So this is what we call CO. And we are looking for the distribution in the ring, basically. It's a hollow cylinder. So if you insert that, and then again, remember that this is only due to elasticity, basically, this linearity of the stress is basically only due to elasticity. So if you do that, and if you replace tau max by tau y, then you can calculate torque as tau y times j divided by c, which is exactly what we had before. So this is what we did here. Alternatively, this is what we just did in this lecture. What we had here is what we had done in the previous lectures. So the reason I'm doing this is that for the part B, we can no longer use this one. So our previous approach is valid for part A only because it's elastic. But for part B, we have to use this sort of alternative view. So for part B, I start exactly with the same formula, with our generic formula, except that now because we want to have the maximum plastic torque, we just replace tau, the torque, by yield stress. And if you do that, you calculate the maximum plastic torque, 4.11 kilonewton meter. That's obviously more than the maximum elastic torque. Okay, so we have done part A, we have done part B. Now, in part C, we want to know what is the gamma at the outer radius such that we have a fully plastic deformation. Now, if it is fully plastic, the stress distribution, the shear stress distribution would be like this. So it's just a constant stress. This is the stress distribution. But if you remember, we said previously that the strain distribution is always linear. So strain distribution, it follows the geometry. It doesn't know about the material behavior itself. It follows the geometry. Now, because you know it's fully plastic, it means it should be plastic already at the inner radius. So it starts plasticity here. And then, you know, if this point is plastic, and because it is a linear distribution, and you know everything beyond this point is more, or it has a more, it has a larger strain, that means if at the inner radius you just reach plasticity, at the outer radius is definitely also plastic. So that's how you should look at it. So basically, the plasticity is complete, or you get a fully plastic deformation, if at the inner radius, so where the gamma is minimum, so your gamma minimum must be 0.286 times 10 to the minus 3. So if the minimum shear strain is exactly what you have here, then obviously any point beyond that, it's also plastic, and you use exactly that relation. So basically, you have the ratio 0.286 times 10 minus 3 at the inner radius equals what value of shear strain divided by the outer radius. This is what you want to calculate. So how much shear strain do I have at the outer radius such that at the inner radius I have 0.286 times 10 to the minus 3. And if you calculate that, you get 0.477 times 10 to the minus 3. So that's it. That's the also answer for the part C of the exercise. So we are done with the topic torsion. We had 4 lectures on this topic. The take-home message for you is that torsion, similar to axial loading, it follows exactly the framework that we are looking for in this lecture. So basically, if you remember, we always talked about this big picture of mechanics. For axial loading, the question is what is the relation between delta and P? And that relation turns out to be delta equals PL over EA. For a torsion problem, we are looking for a relation between the angle of twist phi and the torque T. And the relation here is phi equals TL over GJ. And then again, this is basically for elastic relation. So what you see here, we already assumed the elasticity, but we also talked about stress concentration and we also talked about inelastic deformation in both topics. So you should start always from elasticity and then you can add more complexity to it. Again, similar to before, it's very important that you see that every parameter that you have for an axial loading problem, it has its own counterpart for a torsion problem. And also their dimensions matter. So for instance, strain here for axial loading, it's dimensionless, it's delta divided by L. For a torsion problem, the strain is the shear strain, but it's also still dimensionless, but now it would be phi angle of twist times radius divided by L. So instead of delta divided by L, you have phi times R. Stress-strain relationship, gamma equals E epsilon, would be corresponding to tau equals G gamma. And the stress formula, which previously it was just normal force divided by area, it's now slightly more complicated. It's T torque times radius divided by polar moment of inertia. All right, so this was our fourth and last lecture on the topic torsion. We covered sections 5.8 and 5.9 of the Hibbeler book, corresponding to the fifth chapter of the book. And in particular, we talked about stress concentration and inelastic torsion. From the next lecture, we will be talking about bending problem. I'll catch you in the next one.